Hello everyone, this is Jeff from the Ozark Mountains, that's in Missouri, in the USA. Today we're going to take a look at using a vintage DOS assembler for multiple 8-bit microprocessors with a modern IDE. This will allow us to assemble code for multiple microprocessors while only having to learn one assembler syntax. And all of this with the ease of a modern integrated development environment. How is all this possible? Well, stay tuned and we'll jump right in and find out. Here are just a few of the circuit boards I've had made recently by PCBWay, who is nice enough to sponsor this video. So whether you need a few boards or a lot of boards, check out PCBWay. So head on over to PCBWay and get your instant quote on standard circuit boards, flex circuit boards, assembly, and they now also offer rapid prototyping, so you can get your mechanical parts made as well. That's an awesome service. So for your next project, head on over to PCBWay. I'm sure we've all heard the terms machine code or machine language or assembly language before, but what do they really mean? All microprocessors understand a limited number of instructions, which we can think of like their own unique language. There are many different types of processors, and they all speak their own language, or code if you will. If you were learning to program back in the 1970s on something like this Altair 8800, you'd most likely start out by writing your own programs by hand on paper and hand assembling it. The Altair used an Intel 8080 processor, so you'd be programming in 8080 machine code. To make programs easier to write and think about, short names were given to each instruction. Instead of having to write out your program as just a bunch of numbers like 3A0100, a mnemonic such as LDA01 could be written. This is more of a human language readable form and easier to use and to think about. After writing your program out using these handy opcode mnemonics, you would use the table to look up the numerical value of each one. You would look down the table to find the LDA instruction and discover its value was 3A. This process is often called hand assembly and was also quite common, and is one of the ways I learned to program the 6502 and 8080 processors back in the day. Programmers then had the idea to write assembler programs to make writing machine code easier. You could type out your program in a text editor and then run the assembler, asking it to assemble your program. The assembler would automatically convert the text to the proper numerical values. This made machine code programming easier and less error-prone. The assembler program could even be written to run on a computer using a different type of processor than the one you were targeting. This lets you use a bigger, faster computer to write programs to run on a smaller system. This is what is referred to as a cross-assembler. Programming using an assembler became known as programming in assembly. There is another type of programming tool similar to the assembler called a machine language monitor. It's designed to run on the same computer system you're programming for and provides a more interactive programming and debugging environment. A monitor program lets you examine and modify memory directly, as well as discover the state of the processor flags at various points in your program. The key point here is that whether you're writing your programs on paper and assembling them by hand, using an assembler program, or a machine code monitor, you're accomplishing the same task. You're programming the computer directly in its native tongue. You're simply using different tools. Of course, there are different types of assemblers too. Let's say you wanted to write programs targeting the Motorola 68HC11 processor, so you might use the assembler program that Motorola offered. It works for a few members of the 6800 family and uses its own unique syntax. If you then needed to write some code for 6502, you would need to switch to a completely different assembler, but odds are it will have a slightly different syntax than the 6800 assembler. Somewhere along the way, someone figured out that rather than writing a unique assembler program for each unique processor, they could write one program that looked up the conversion from mnemonic to opcode value in a table. Each processor type would have its own table that specified this relationship. You could even add support for new processors by just creating a new table. Best of all, you only needed to learn one assembler syntax. This sort of assembly program became known as a table-driven assembler. From the late 1980s until the early 2000s, there was such a table-driven assembler written for DOS and Linux available as shareware called the Telmark Assembler. It could be freely distributed, and when you sent in your registration fee, you were sent a disk with the source code as well. Thanks to the magic of the internet, we still have access to TASM today. I was introduced to TASM just last year by my friend who makes the TRS-80 Model 100 test harness. It is what he used to write the test firmware, so it seemed like it might be worth learning about so I could customize the test firmware myself. I was a bit worried about trying to get an assembler written for DOS to work properly under Windows 10, and also concerned about how easy it would be to figure out. Much to my surprise, I found TASM was easy to use. The command line interface made sense, and it strikes a good balance between power and ease of use. Some assemblers I have tried put a lot of effort into trying to be clever and incorporate lots of assembler tricks, which just makes the other 99.99% of what you need to do more difficult. My friend who created the M100 test harness had included his batch file he used for TASM, which helped get things going quickly. Soon I was writing code using Visual Studio Code as a text editor and assembling it via the command line. I even tweaked the batch file to suit my own needs, and then I really went down the rabbit hole and got to wondering what it would take to create an extension for Visual Studio Code that supported TASM. Learning how to create an extension for VS Code is complicated by the fact that there are many different ways to do so, and that the reference information seems to be either overly vague, hand-wavy type of explanations, or overly specific about some nitty-gritty detail that had nothing really to do with what I was trying to accomplish. I finally stumbled upon a Z80 highlighting extension that was simple enough to grasp what was going on. From that starting point, I was able to get syntax highlighting mostly working for the 8085, and after a lot more trial and error, it was working quite well. Then it turned out to be fairly easy to create a syntax highlighting for a new processor. I'm sure that the syntax highlighting is not perfect, and I have tried to use standard VS Code scopes, that is, categories, so it should work with any custom theming you might be using. Any feedback would be most appreciated. The next step was to get problem matching working. Problem matching describes the functionality of VS Code to be able to parse the error output of TASM and allow you to click on a reported error and be taken to the correct line of the file. Thankfully, TASM has a consistent error output statement format that was not too hard to parse, even with my limited knowledge of regex statements. In fact, it came down to this one little line right here. Now problem matching was working well too. At this point, I was manually building from the VS Code terminal by calling my batch file build.bat. VS Code has a built-in shortcut key combinations that are configurable. It was fairly easy to figure out how to configure the build shortcut, but it still eludes me how to set this automatically through the extension. This is very easy to set up manually though, and we'll cover that in a bit. I am not an expert at VS Code or VS Code extensions. This is very much a work in progress, but it works well and it makes for a nice development environment. Again, any feedback is welcome. Well, now let's see how to get this set up on your computer. I wrote a PDF which describes how to set things up, but let's go ahead and go through it here together. Of course, you'll need to have Visual Studio Code installed. Installing the extension is simple and can be done through the VS Code Marketplace, or you can do it manually. Even if you install through the Marketplace, I suggest downloading the project from my GitHub account. The links to all this is down below. This contains the PDF as well as some example files in the suggested directory structure, TASM 3.2 for DOS, and some extra processor tables. To install the extension, we can either go through the Marketplace or we can do it manually from the files we downloaded. Either way, we open up the Extensions tab, and if we want to go through the Marketplace, we can just type in TASM here, and it'll search for it, and there we go, TASM Assembler 0.6.0 from Soi Generis, and you click Install here. If you want to do it manually from the file set you downloaded from GitHub, you click on the ellipsis up here, Install from Visix, and you navigate to the files you downloaded and you click on the physics file. This installs the same code. And we can see down here at the bottom now, we have the TASM assembler extension installed. With the extension installed, we can go ahead and minimize the extension tab, and we'll take a look at the suggested directory structure. The GitHub project contains this suggested directory structure, which consists of two main folders, projects and TASM. The projects folder, of course, is just a space to keep all your projects, and there's one for each different assembly project that you're working on. There's also a TASM folder. It contains TASM 3.2. This is the assembler itself with all its built-in tables and its documentation. And there's TASM tab, which just contains a few extra tables and some notes about those, where they came from, what they're for, and that type of thing. We take a quick look at one of our example projects. For instance, our HC11 project, there are some notes which we can look at. And go ahead and use VS Code for that. And the notes will just be a bit of an explanation about what this code is and where it's from. This one happens to be some HC11 code that I wrote 20-some years ago, and I happened to find it, and just to see what it would take to convert it from the Motorola format to the TASM format, and it really wasn't that difficult to convert. If we take a look at the build.bat file, build.bat is a batch file that kind of automates the process of assembling your project and just makes it easier. The first thing we do is set an environment variable which tells TASM where it should find the table to use for this project, and here it is in the main TASM folder, TASM 3.2, so we're using one of the built-in tables. The next thing we do is call the TASM assembler itself with a number of options. G2 means we want a Motorola hex output file, which is like an S19 file. -68 tells it to use the 6800 assembly table. The -X7 says, hey, we need to use the extension for the 6800 table to allow us to do 68HC11 code. And this is our source file name. And then we're going to delete any previous S19 files, and we're going to rename the object file that TASM output to an S19 file. An S19 file is sort of like Motorola's version of an Intel hex file. Of course, for other projects, your build.bat will be a little different. You'll have different options, and you might do other things, as we'll see later. Let's say we want to go ahead and assemble our 68HC11 project. The first thing we need to do is set up a workspace in Visual Studio Code. A workspace is just a way that VS Code keeps track of where all the files for this project live. To do that, we click on File, and we make sure that there's no current workspace active. If there was, there would be a choice down here that says Close Workspace. So since there's not, we can go ahead and click on Add Folder to Workspace. And I'm going to select this is the projects folder I downloaded. I'll select that I want to create our workspace in this HC11 project. I'll click on Add. And now we've got our workspace created. And the next thing I like to do is go ahead and do a Save Workspace As. And I like naming it as something similar to the project name, 68HC11 example. How about that? With all that taken care of, you go up and click on your workspace tab here. It'll show you everything that is in that workspace, and we can open up our assembly file, as simple as that. And this is the whole program. And as I recall, all this program did was test out a keypad and LCD combination I had hooked up to a little 68HC11 development board. And all I really had to do to convert this from the Motorola assembler format to TASM was change all the comments to a semicolon. The assembler directives all needed a dot before them. The assembler directive for byte and text and things like that were a little different, but it wasn't too bad. And the nice thing is now is that the syntax for this file is the same as it would be for 6502 or 8085, so it makes it a lot easier to switch in between projects with different processors. Now, before I tried to build this, I'm going to go ahead and set up my build shortcut key. If I press Control Shift and B, it's going to tell me that there's no build task set for this particular project. So if I click on Configure Build Task, say Create it from Template, and just click Others, it'll pop up a generic task.json file. And in the file set from GitHub, there is an example task.json. And if I go ahead and open that guy up, and I'll just do Control A, Control C, and I'll go to the task.json for this project, do the same thing, Control A, Control V, and now I've copied everything over. And it should just work. We can go ahead and close that down. Just so we can see everything that's happening, I'm going to first open up a new terminal, which will open up on the bottom of the screen here. And you'll notice that our working directory is our project directory, which is convenient and it's good, which means that our batch file is going to run with that as the working directory. I'll do Control Shift B again, and it just assembled our program and created the S19 file. If we look back in that our project directory, we can see that indeed we do have an S19 file, which is the binary code, and we also have a list file. If we take a look at our list file, this is kind of like the combination of our source file with all of the actual binary code for each line. So it tells us the line number, the address, any code that it assembled at that address, that type of thing. This is kind of a handy reference for debugging and things like that. This was a fairly simple example, and I know that this worked and everything was going to build fine and there would be no errors. So what happens if there is an error? Well, that's where the problem matching comes in. Let's go ahead and start up another project, and I'll go through this one kind of quickly. I'll close down these files, and I'll ask Visual Studio Code to close this workspace. I'm going to add a folder to the workspace. Go to my example directory structure projects. This time I want to do the example 8085 project. And I always like doing save as immediately. Example 8085. That's as good a name as any. And if we look in our workspace here, here's our code. This is just the example source code from the TASM folder. I purposely created an error in so we could go through it and find it here. Now, if we do Control Shift B for this project, we're going to run into the same thing. We don't have a task.json set up for this. So again, we'll just go through this and set it up. We only have to do this once. And we'll grab our example. I'm sure there's a way to automate this. I just haven't figured it out yet. Bring up the terminal so we can see it as it goes. Control Shift B. And it's going to build. And this time you'll notice that TASM is telling us that there was one error. And it's saying it doesn't recognize the instruction. And you'll notice here where it says problem, it's got a 1. That's our one error. If we click on this Problems tab down here, it'll tell us the file and the line number. If we click on that, we're taken right to it. And oh, you know, silly us, we meant to type in MOV, and instead we typed in MVO, and We might have noticed that when we did it because the syntax highlighting wasn't right, but we can fix that very simply by doing that. And we can see by the syntax highlighting that was a recognized mnemonic. We can save our file. We can go back down here and just press any key to close that down. Control-Shift-B again. And this time we built without any errors. And, with TASM's output, we could have found the file in the line easy enough, but it is so nice and quick and easy just to be able to click on each problem and go to it automatically. Now, for a more complicated example, let's take a look at what it would take to write a program for a Commodore 64 and launch it in Vice. So again, we'll go ahead and close down our existing project, close Workspace, and I'm going to do a File, Add Workspace to Folder, and there's our directory structure projects, and I want our example C64 project. And like I said, I always like doing a save as right after that. Call this example C64. Our goal is to create a program we can load onto a C64 and run. A C64 program file, a .prg file, has a 2-byte header that tells the C64 where this program should be loaded into memory. We need to find a way of asking TASM to output these 2 bytes into the output file before our actual program code. I chose to use the starting address of 0801 as it is the start of basic memory. This was done to illustrate the method of including a line of BASIC at the beginning of your machine code program. The purpose of this line is just to provide an easy way for the user to run your machine code. In TASM, like other assemblers, we use the .org directive to tell it where in memory our code will live. When TASM sees a line like .org 0801, it knows that the code filing will live at that address in memory. Since we want to sneak in our 2-byte header at the beginning of the file, we can use the line .org 0801-2, which will tell TASM that the following code will live at 07FF. We could have also just written .org 07FF, but using .org 0801-2 provides a clue to others, and ourselves later on, as to what we're trying to accomplish. We then use the byte directive to insert our 2-byte header, the starting address, in low byte, high byte order. The next 2 lines of byte directives are actually a line of basic code that says 10sys 2304. This is not actually the text or the characters, but rather the tokenized basic line, just as if you had typed it in and hit enter. If we could skip ahead in time and look at our finished program in a hex editor, we could see this. Luckily, we don't have to time travel to do this. Besides, my DeLorean is in the shop. Even flux capacitors start to leak after 30 years. We can see in the hex editor that we have our 2-byte header in low byte, high byte format, and then we can see our tokenized line of basic code. But then you'll notice a whole lot of zeros. Where did all those come from? Well, let's look back at our source code and find out. Next up in our source, we have a line that says asterisk equals 0900. Well, this is just another form of the .org directive. It's just saying that the code that's following should start at this address. This is quite a few bytes from where our 1-line basic program left off. When we assemble our code, we'll need to ask TASM to fill in the blanks. That is, write out some zeros into the file to take up the space between 0811 and 0900, giving us one contiguous file that can be loaded into the memory of our C64. Our actual machine code program lives between the start and exit labels. It just copies a section of our program memory into the screen RAM. On computers that use ASCII, we could have used the assembler directive .text to convert our text to the corresponding ASCII values. Our C64 uses PETSCII, however, so we need to convert the characters to their PETSCII values manually and include them with byte directives. If we look back at the hex editor now, we can see that after all that padding of zeros, we have 2 lines of our machine code program and our PETSCII characters. So how do we configure TASM to build a C64 source file like this? Let's take a look at the build.bat and find out. First, as we normally do, we tell TASM where to find the table that we're going to use, which is just the standard 6502 table. Now down here where we actually call TASM and ask it to assemble our program, we're going to pass it a few different arguments. One is -C, which gives us a contiguous file output with all of that zero padding. The -G3 gives us a binary output. Well, actually, if we just included the -G3, that would be fine as the C is implied there, but I did it this way just to make it clear what was going on. The -65 just says we want to use the 6502 table, and of course, this is the name of our source file. If we build this project right now, TASM would happily create a .prg file for us. Note, however, these last two are marked out lines. If we unremark this line and change this path to Vice, to our actual path to our Vice installation, here's one I prepared earlier, then when we build, Vice will automatically be called with our .prg file. Let's go ahead and save this, and then we'll give that a try. Switch back to our program here, Control-Shift-B. And it looked like we built okay. And here Vice started up, and it ran our program, and we printed Hello World on the top left corner of the screen. Excellent. TASM is very versatile and can be used to create code for many different processors and types of computers. You could use such a tool to develop for multiple 6502 computers using the same code base by making use of conditional assembly directives like if-def to include the correct machine-specific bits for each platform. You can also develop for multiple platforms while only needing to learn one assembler syntax. There are also development tools dedicated to one particular type of computer. For instance, CBM Prg Studio for the Commodore 8-bit 6502 machines. A dedicated tool has the advantage of knowing all about the target machines. For example, CBM Prg Studio already knows how to create a PRG file and start it in Vice. You don't have to set that up manually. Quite often these dedicated tools will have other things built in like character and sprite editors that make life easier. Both types of development tools have advantages and disadvantages, and it's great to have multiple options so we can pick the best tool for the job at hand. I'm hoping that by providing a starting point and some tips, it'll encourage others to give writing some machine code for their computers a try. Our beloved old 8-bit machines are fairly easy to learn on, and everything is just simple enough that you can kind of grasp it all in your head. Writing in assembly code gets you closer to the metal. You get to learn a little more about what makes the microprocessor tick and how it works with the rest of the computer. Even though I enjoy programming in C and C++ and BASIC and such, I also still really enjoy programming in assembly. One interesting side effect is that sometimes you discover new ways of accomplishing something, say in C, based on some earlier programming that you've done in assembly. There were lots of books written on machine code programming back in the day. Here are just a few I've collected over the years. This is probably the first one I ever had, bought for my Commodore 64. The great thing is that today, while books like this are getting more rare and more expensive to buy, they've all been scanned, and you can download a PDF of them from places like archive.org. In the future, I'll be adding syntax highlighting for other processors that TASM supports. I would also like to develop a table for the Sharp LH5801, which is a Z80-like processor that was used on the Sharp PC1500 and Radio Shack PC2. Since it's so much like the Z80, I think using TASM's Z80 table would be a good starting point. And it should be an interesting learning project. Well, I hope you've enjoyed this episode, learning how to take a vintage DOS assembler and using it with a modern IDE. Learning how to create the VS Code extension was certainly an interesting experience. So download the extension and the files from GitHub and give it a try. Thanks to everyone who helps support the Hey Birt channel through Patreon and other means. It's greatly appreciated, and you keep this whole thing going. If you'd like to find out some more information about becoming a supporting member, well, look in the description down below. There's some links there. There's a few perks involved, like early access and ad-free videos. If you have any questions or comments, well, just leave them in the comments section down below. I would love to hear from you. Remember to like, share, and subscribe. And until next time, bye.